So at the earlier session I gave you a hint about a way forward to find some kind of mathematical criterion for distinguishing whether a pair of observables are compatible or incompatible. And that strong hint was to make two measurements on a quantum system, so general wave function psi, and to measure, so your two observables are A and B. So first was to measure A and then immediately measure B, or to measure B first and then A, and look at the resulting wave function that you get. If they're the same, so if AB gives you the same as BA, then A and B are compatible. And if AB gives you something different from BA, then the two observables A and B are not compatible. Now that's the sort of a hint. Now let's try to pursue that direction and get some more concrete, more rigorous math out of it. Okay, so we have two observables A and B with their corresponding operators A hat and B hat. So here are the two eigenequations for these two observables, for A hat and for B hat. And let's maybe take a mental note that the eigenfunctions for A are psi, and the eigenfunctions for B, or B hat, are phi. Okay, so psi and phi, so you know which is which. It could get confusing. When we talk about these wave functions, we're talking about phi or psi, and we're talking about A or B, because it can get confusing. All right, so let's measure A, observable A, first. So we're talking about this eigenequation, okay? And we're assuming our initial state, before we do the measurement, is psi. It's just a general wave function, whatever. All right. Now, we can expand. We can rewrite this psi as a weighted sum. A weighted sum of which form? Do I have it written here somewhere? Yeah, here. If this term here is just a general wave function, you can always write it as a weighted, by complex numbers, a weighted sum of the eigenfunctions of the operator you're talking about. So, well, in this case, this phi is talking. We're talking about operator observable B, but in general, you can express a general wave function as a weighted sum of orthonormal eigenfunctions of the observable you're talking about, the corresponding operator of the observable you're talking about. Okay, so now say psi k is one of these eigenfunctions of observable A. We're talking about psi here, right? So it's one of these, and we get, when you perform the measurement of observable A, you get this result. Let's say lambda k. So it's the kth possible value, discrete quantized value of this observable A. Okay, lambda k, and its corresponding eigenfunction will be psi of k. Okay, so your general wave function that before the measurement is psi, then collapses to psi of k, because the measured value you got was lambda of k. Right? So psi collapses to psi k. Alright? Now it's a big if. Right? So I put big letters here, big if, doubly underlined, strongly conditional. It's a big if. If this psi function here happens to be one of the eigenvalues, so this eigenvalue for measuring A, if it happens to be one of the eigen functions for B, right, then if when you come to measure B, you will get with certainty, now concentrate on what I'm saying, because it's rather dense reasoning, but verbal reasoning for the time being, sort of like philosophy. Okay? So if the result that you get here happens to be one of the eigenstates, the eigenfunctions of observable B, because that's the measurement you'll do second, right? We're doing A and then B, right? So if that's true, if the eigenfunction, the eigenstate that you get after you do measurement A, if that happens to be one of the eigenstates of B, then you will get the measured value for B as one of these mu's, let's say mu k. So if it's phi k, with certainty your measured value will be mu k, right? It'll be, so if you're getting phi k, so this n here is k, so it'll be mu k here. You will get that with certainty, okay? And then, and the state will remain unchanged, because if psi k is equal to phi k, right? If you perform a measurement B on phi k, with certainty you'll get mu k, and this wave function here does not change. Right? That's typical of eigenstates. If you know your wave function that you start with before the measurement is an eigenstate, an eigenfunction of the observable that you're measuring, then for sure you will get the same wave function after the measurement. Your psi k before is the same as psi k, it's the same psi k after the measurement. That's typical of when your wave function is an eigenstate. Right? You only get collapse when you've got a superposition, right? When you've got your coefficient c. But if there's only one eigenstate involved, if there's no superposition, there's just one state, one eigenstate involved, then the measurement outcome is certain, and the wave function does not change after the measurement. Okay? I hope you knew that already. We've talked about that before. Okay. All right. So your eigenfunction here, this is what you get. See, these two are the same, right? We're assuming that. This is the big if. So these two are the same. That's what you get after measurement A. But we're assuming this is equal to one of these eigenfunctions. Let's say phi k. So after measurement B, the state is still this, phi k. But phi k and psi k are the same. So if we now do a second measurement of B, in other words, a third measurement, so A, B, A, okay, then the result of the second A measurement, so A, B, A, will still be this. Can you see why that's the case? Because what's your wave function, what's your state after the B, after the second measurement? Well, it's phi k, right? But phi k equals psi k. So if you do a measurement A, like the second A measurement, in other words the third measurement, A, B, A, so if you do a second A measurement, you will get lambda k again, right? And then if you do a second B measurement, in other words the fourth measurement, A, B, again you will get mu k, right? Because the state doesn't change, it just stays, it stays here, it stays at that one or that one. But these two are the same, so they're in the same state. So in other words, you can measure. So if, it's a big if, but if this is true, if this is equals one of these, then you can measure A and B, A, B, A, B, A, B, and get this, and know what you will get you can measure, in other words, you can measure A and B with all the accuracy that you want. You'll know with certainty you'll get this value here for A, and you will get this value here for B, right? So you know with precision the values of these two observables, A and B. They are lambda K and mu K, right? So we have a criterion now for compatibility. The compatibility exists between these two observables, A and B, if the result of your first measurement, so measuring A, observable A, if the result, the resulting wave function, the resulting eigenstate, let's say psi k, if that psi k is equal to one of the eigenstates of B, if that is that, then A and B are compatible. Okay, hope you followed that logic. It's a multi-step logic, but now we've got a criterion for compatibility. Okay, it's just when this equals that. All right. Now the other case. I've got here. But what happens when the eigenstate that you get for A is not equal to one of the eigenstates for B? What happens then? Well, you'll go. So you've measured A, right? You've got this eigenstate psi k. That was the result of measuring A, and now you're going to measure B, like the second measurement. But this time, the result that you got, the resulting eigenstate, which is psi k, it is not one of these eigenstates of B. So what's going to happen now? Well, so from the point of view of measuring B, this eigenstate of A now is just the general wave function.